Hi, how are you?
Hey, Katerina.
I'm using Clubdeck today because I want to open also a Twitter Spaces room. So um, I'm trying it on.
How do you do that?
So I have to use two devices. That's why I'm using. I couldn't figure out how to use Twitter Spaces on the desktop, but I at least have a Clubdeck, um, on the desktop. So I'm sorry if I'm a little bit slow at responding here on the on the Clubhouse site, but I'll try it at least. So we'll see. I oh, now you're moderator. I thought I did that already.
Let me know if something I can be helpful.
I don't know how to ping people in Club Deck.
You click on the if you have the update version, click on the little box, the lower left in the middle. There's a rectangle with an arrow up. Then you click that. It's basically a sharing function. At the bottom, you see
Oh,
the
okay.
invite people.
Totally you. Inviting you to be on the stage. I'm not sure if it's working. If not, Frank, could you also invite Dr. Liu to the stage?
Yes, I did.
Can you see the invite, Dr. Liu? Um, it should appear on the top of your screen, a green message, accept. Yes, there you are. How are you doing?
I'm doing well. How are you?
Very good. Thank you so much.
Do you hear me okay?
Yep, with a little bit of feedback though, but
I think it's because I probably have to zoom here too. Just 1 second. Let me turn this off. Okay, is it better? Oh, still echo. Let's see. Uh, it must be because of this one. Just a second. I need to change the setting here. The audio too. Okay, now it should be okay, right? No, still echo. Hmm. Take this off. How does this look? Oh, still echo. Hmm. Maybe it's because of the zoom I have. Let's. I know this. Set this one. Change preference audio to this one. Now it's okay.
Usually, if you have two like devices at the same time, and then muting one mic, leaving one mic unmuted probably will be helpful.
Yeah, I only have one mic on now.
Yeah, we're getting echo.
That's right. That's right. Let's see. Maybe I just turn off my Zoom. If you turn off Zoom, see how it works. Just 1 second. Assign. Okay, do you still echoes? Still
Still
echo.
echoes.
That's still echo, right? So let's turn this off. How about this?
Oh, that's better.
Looking good?
Mm-hmm.
Let's see. 我去了那个了，已经。让我看啊，audio setting default. I have to get one of them on. This looks like. I have to get this on. Okay. Do you see his echoes?
I think there's still some echoes. I was very curious how this was going to go.
Yeah. I did turn off my. Maybe I should not use. Let me just. If I use my display audio. Is this better?
I think we're still hearing echoes.
I think it's better. Yeah,
A
on my
little
side
better,
anyway.
yeah.
This one. Is that good?
Now it's kind of just reverb.
I think that's what I used last time with Katrina. I turned off the no zoom now, so I just did the audio I have.
I think this is okay. It's
Isn't it okay?
yeah, I think so.
Oh, why
Yeah.
did we have this echo last time?
No, I
When we
don't think
tested
so. I don't think I heard any echo last time. But
input mic display audio. Yeah, that's a usual. That's what usually I have. I have this I have two systems, but I can select each one of them. I selected my now display audio, display microphone. But it's not you don't hear twice, right? Just the sound is like in a big room, right?
Yeah, it's
Okay.
Yes, reverb.
So in that case, I probably can still switch my. Let me just let me switch on my Zoom. See if it become worse or not. I would think it should be same, right? There's no change, right?
yeah, it's
Do
not
you
a
hate any difference?
no.
Okay, so that's good. So we keep like this. So now I have Zoom and the Clubhouse. Okay.
Yeah, perfect. Thank you so much.
Okay, you said you're going to record. Can I record it too?
So I will send you the recording after this. It makes automatically a link where you can go to and listen to, and then I'll also explain to you how to download the recording. There's a way to go on the link and then download recording. Then you send yourself an email with a link, and then it downloads from the S3 from Amazon account from Clubhouse.
Okay,
And
so what I'm going to do is that I'm also recording on Zoom too at the same time.
okay, yeah, sure.
So in Zoom, when I record on Zoom, then I can get video too.
Yeah, perfect. So I also opened up a Twitter Spaces from Science Society just to, also to try it out today, in case people are interested. But yeah, it's just to try out different platforms, and yeah, it's exciting. So anyways, let's start the room. So welcome everyone to Science Society. We are very honored to have Dr. Liu here with us. And let me tell you a little bit about him. So, you know, some facts about our guest speaker. Um, Dr. Liu is the Dorothy Pate Enright Professor in the Department of Material Science and Engineering at Pennsylvania State University. He obtained his Bachelor in Science from Central South University in China and his Master's from University of Science and Technology in Beijing. And then he uh, obtained his PhD from Royal Institute of Technology in Sweden. And later on, he was a research associate at the University of Wisconsin-Madison, and then a senior research scientist at Questek Innovation LLC. He has been at Penn State University since 1999, and he's editor in chief of the Kalfat Journal since 2001, and the president there too. And he founded the NSF Center for Computational Materials Design and served as a director from 2005 to 2014. Dr. Liu coined the term materials genome in 2002, and he served also as a president of ASM International and a member of ASM International Board of Trustees. And he received many awards, including the William ASM J. William Gibbs Face Equilibrium Award, the TMS Hume Rothery Award, and the Wilson Award for Excellence in Research from Pennsylvania State, and many other awards. And Dr. Liu's current research activities are centered on first principle of calculation, machine learning, modeling of thermodynamics, kinetic and other properties, and the integration of understanding defects, phase stability, and phase transformation, and designing and tailoring materials, processing and properties. Yeah, so we are very honored to have you here. And yeah, thank you so much. The stage is yours.
All right. Thank you very much, Katerina, for this opportunity to have some, little casual discussing about what entropy and Zentropy are, and why they're important in science. Let's see. Okay, I do have a PPT file. So I think Katerina sent the link to everybody. I hope you have downloaded it. So I'm going to say the slide number when I go through the slides. Okay. So the slide 1 is the title slide called Zentropy.
We don't have the paper yet.
Oh, you don't have the paper yet, the PPT file? Katerina can send the link. The link should be.
Yes, 1 second. It didn't work. Let me see.
While we're
Oh, the link did not work.
while we're working out.
Oh, now,
okay,
now
there we
you
go.
Okay. I'm on club deck today, so I'm sorry.
It's okay. So can you if you click the link, it should be able to download the PPT file. All right, should we continue?
Yes, everyone should be able to see it now. Thank you.
All right, so I'm on this first slide. Zentropy. My name is Zi-Kui Liu. As Katerina said, I'm teaching at the Pennsylvania State University. This link, www.faces.psu.edu, is our group website. Now I go to slide 2. So Z plus entropy is equal to Zentropy. So this term was suggested by Josh Roberts. He's from the University of Buffalo. I gave a talk in June 2022, talk about our approach. And I said we're looking for a name for the approach. And at the end of the talk, Josh said, maybe Zentropy would be a good name. Then we actually liked it a lot. He explained why Zentropy. This is showing here the link YouTube video. That's recorded at a seminar. It's about 1 hour long. It's actually at about 1 hour time. That was Josh made a suggestion about the name. If you look at the YouTube, you just quickly go to 1 hour, then you will hear that he suggested.
So yeah, but just quickly, entropy is related to the partition function.
Yeah, that's right. That's my next word here, right? Hey, that's exactly, why it's Z. Yes. That's why we use. That's why he searches Z, right? Z is Zoom's Zoomi, sum of states in German, and it is for statistics mechanics, as think as Eric just mentioned that. It's about a partition function. It's used for a long time, and it's about probability of states. So that's basically what Z really stands for. Statistics mechanics means this field. Partition function is the mathematical representation, and it talks about the probability of states. So then the Zentropy is really actually talks to all three of them. Talk about the statistics mechanics, talk about the partition function, and talk about the probability. So we love this name, so we started using it. So the name is not very old, as you can see. It came up in June last year. Okay, so let's go back to entropy first. Right? Entropy is multi-scale. So what does it mean? I guess many of you have read this book or listened to this book by Stephen Hawking, The Brief Answers to the Big Questions. And this is black hole. This is the cover of his book. And in this book and his other publications, he talks about the entropy and information of black holes. So black holes have entropy and you have information. So entropy and information go hand by hand. So this is a big scale, right? If you go to a little bit smaller scale, you talk about the human society. It's the order of time. Okay, it's another book. It's really very interesting book. Both are bestseller, as you can see. And in this particular book, this author made some very, very, very interesting statement. Well, of course, I agree with his statement. That's why you say entropy drives the world. And everything is basically driven by entropy. So time slows down when moving faster. And then, of course, you probably heard that if you move as fast as light, right, they live forever because time doesn't disappear anymore. So
Or you get
that's
pulled to pieces. This is a theory we have yet to see in action, right?
That's
For
right.
humans.
Absolutely. Yeah, because you cannot imagine how you travel as fast as the light, right? Okay, that's a very good point. All right, so you can see different scale, right? Of course, I'm a material scientist. I don't study the black holes. I don't study the society. So I study materials. Okay, but it's a very interesting book. So now it's closer to this one, to the materials we study now. So this is a book by Ruth Spiral for kids. She wrote a lot of books for kids. One of them is Baby Loves Thermodynamics. Babies do all kinds of things, right? But one of the things do actually, not only baby, everything we do is processes. Every process we have, it should produce entropy. So one of the big processes we have is the sun, the light, the energy, right? Heat comes from the sun, So what happens here? You get the sun comes the energy from the sun, right? And then the sun comes reacts with air and water, then produce trees, right? Food, apples, whatever. So it's all by that one. So I call this process one. It's light from sun to earth. So that process is entropy production. Yeah, we talk about it later, why it's entropy production. The second process is kids. We're talking about kids here. The kids make a mess of a house. Anything they do, they make a mess, right? So that process produces entropy. So that means the kids actually, they're natural. They act naturally to make a mess. Why do they make a mess? Because the entropy is produced in that process. So this is, if you learn more on thermodynamics, this is basically the second law of thermodynamics. It says that any process, they are irreversible, they produce entropy. Okay, that's second law of thermodynamics. All right, so this is the basic the theory we have. Then we're gonna you apply them, right? We're gonna apply them. So if you have learned the thermodynamics before, you know that entropy change is equal to delta Q divided by T, the heat divided by temperature. Okay, so let's apply the heat from sun to earth, right? So that means we have two entropy change. One is the entropy change of the sun, another entropy change of the earth, right? That added together, that's the process of the heat. It comes from the sun to the earth. So now we know that the sun has high temperature, earth has low temperature. And I'm not at slide, I'm sorry, I'm not at slide 5 already. Oh, gee, I'm at slide 5 now, sorry. Yeah, I should mention about slide number. I'm at slide 5 now. All right.
That's
So now,
the one with the title of entropy process. Is that the slide?
yeah, entropy process 1.
Okay, thank you.
Yeah, entropy process 1, sorry, that's right. And so what happens there is that you see that because the sun has high temperature, so delta Q, that's the number of heat taken from sun, divided by high temperature is small entropy. When the same amount of heat arrives at the Earth has low temperature. So that is a bigger entropy, right? So the heat leaves the sun, so the entropy is decreased, but the sun, the heat arrives at the Earth, the entropy is positive. So the positive minus the negative with a small number, the whole process has a positive entropy increase. Okay, so this process is follows the second law and increase the entropy of the sun and earth add together. Because that's one process, right? So that's process 1. So now if you go to, of course, that entropy process, get the energy here, that's where it goes to trees. The tree grows, right? The trees grow and the food, the fruits are produced because that entropy production process. The heat is transferred here and then that's all work. Okay, now we get to slide 6. It's a process 2. Process 2 I mentioned before was that the kids make a mess, right? Okay, so what does it mean? That's S equal to KB log omega. KB is a Boltzmann constant. It's actually the Planck actually got the number, but Boltzmann got the concept. So the value of the number is actually derived by Planck, but Boltzmann has the concept, so we call it a Boltzmann constant. So it's Boltzmann times log omega, natural log omega. Omega is the number of configurations. That is how many ways you can arrange that system. So we give a very simple example. We talk about ice, water, and vapor. Let's just process 2, slide 6. So ice, is kind of solid that we see, right? So you cannot easily deform it. So it has fewer configurations. Water is more fluid. It can go all kind of shapes. Right? You get a lot of configurations. It becomes vapor. It's a big area. So you can see that the entropy of ice is smaller than the water. It's way, way, way smaller than the vapor. So to do that, we have that heat, right? You have that heat, get the ice, it becomes water, and more heat, it becomes the vapor. So that's how you increase the entropy of the system by adding heat into it. Okay, so what does the kids do? Suppose if you go to this figure here, this figure is copied from the internet. So at the beginning, your room it's very tight, right? Very neat. You make the room very neat, and you put the toys here, you put the books there, you put whatever trees there, and that's the left side of the figure. When the kids comes, when your son or your daughter comes, and he or she makes a mess, right? Put everything messed up. Okay, so I have a lot more configurations now. So then to the KB, you have after the kids made a mess, it's a log of capital N, and before it's low n. So this subtracting each other, the total S is increased. Total entropy is increased. The system. So the kids follow second law. Second is the law of nature. Okay? So the kids good. So if your kids don't do that, you need not worry about it, right? That means the kids is abnormal, but abnormal is not bad too, That's genius. Sometimes abnormal at a young age. Anyway, so you can see that when the kids make a mess, it's not too bad, right? It's natural. So then, when in the evening, you just put it back, right? Put it back. But however, you see, you have this log capital N minus log N. But remember, you look at the left side here. You have the blue dots. You have the kind of this kind of purple bricks. Then you have this green triangles, right? So each of them have different configurations. So they have different scales here. So you see, it's not just capital N and the small n, right? Actually, I have more things. You have these dots, you have these bricks, you have these triangles. Okay, so I have more configurations. They're different scale. One is big scale and smaller scale, right? So how do you put them together? So kb log omega is not enough. So you have to consider this one. Okay, so we need a theory to do that. Okay, to model scale entropy. So that's basically what the Zentropy is about. So we need to consider individually and put it back together. Okay, so what it means is that now you talk about a system. Like a system, you have the entropy of the system. First, that you have different microstates. For the previous case, we have 3 of them, right? One of them are the dots. One of them are the bricks, or 4 of them. Another triangles. The third one is this gray kind of blocks. Okay, so it's different. So you have a different way to configure them. So you got this pk log pk. So pk is a probability. So then you learn statistics. Pk log pk, sum of all kinds of possibility together, you got the entropy of the system. However, as I just mentioned, each of the microstate, each of these 3 or 4 of the configurations, they have their own entropy, right? Because we should here just one way, because these dots can be arranged different ways, okay, in that small area, okay, or in the whole big area, you can do that. So each of them have entropy too. So that means if you want to talk about total entropy of the system, we have to think about 2 things, right? One is that all these different microstates configuration, that's the first item, is pk log pk summation. And then each configuration microstate has their own entropy. That probability times its own entropy summation here. So two terms here. So this basically is our Zentropy. So why that's important? Because previously, as I will show you next slide, people only either consider the first one or consider the second one. There has been no theory put them together into one equation. So we see that's a problem. Why the problem? I'm going to show you next slide. Why is that a problem? Of course, that means the problem is that either one of them is not total entropy of the system, right? Only partial of the partial entropy of the system.
Hi, can you explain again why the entropy of the system is that formula that involve the pk?
This one?
Yes, like the
okay. This one is okay. If you go to the previous slide, go to slide 6. That's kp log omega, right? That's what we typically learn.
Yes.
Okay, but this omega, what it means? That means omega means that all the configurations have the same energy. Okay, yeah. That means each configuration has the same probability. However, if each configuration has a different probability, then you get this equation. So you think this one, right? If pk is 1 over omega, then you go back, you get previous equation.
Okay, I see. Okay, I got it.
So this one was derived by Gibbs back in 1870s.
Okay, I got it. Okay.
So when in Boltzmann case, this equation, the equation on numbers on slide 6 is kp log omega. That's Boltzmann equation. Boltzmann consider each state have the same probability.
Yes.
Okay, that's good. That's a good question. Okay, so most of the textbooks they only teach the first one, kp log omega. They didn't teach this one. They should teach this one first. Then say kp omega is out of this equation when pk equal.
Okay. I think it's because the Boltzmann distribution is easier to derive.
Yeah, exactly. But it's less useful. Okay, so that's good. So I'm on slide 8 now, right? I'm on slide 8. Okay. So now you have the two terms now, right? The blue term is pk-sk summation. That means each microstate. Of course, you have many of them, right? Actually, you talk about a big number, okay? And then pk log pk is for the configuration among of those different microstates. And then you think about this one, right? Each microstate could have more finer scales, right? So you can make this Si. Now I'm slide 9. Si can divide even further. So what does it mean? That means this form is so nice. The S equal to two terms are together is scalable. You can think about this when you start from the electron, okay, and then you go to the atoms, then you go to the molecules, then you go to the matters, and then you go to the people, okay, then you go to society, then you can go to the country, then you can go to the planet, then you go to the solar system, then you go to the galaxy, go to black holes. Okay, so it's scalable. That's what we call the nested formula.
So I suppose this is the entropy, relative entropy, computation of entropy from the relative entropy, right? The can have a conditional probability that you can compute the total entropy as the say of two random variables, the x and y, and then the total entropy of xy would be the entropy of with respect to x plus the relative entropy of y with respect to x, right?
So that's actually a very good point. So you have xy, and then you have xy. They have relative probability. So that's why. So the blue term is like x and y separated together, right? But the black one means x, y, they can appear statistically in the system. So they have another probability. Yeah, there's two of them.
Yeah, so the first black term would be, say, the x with respect to the x random variable, and then the blue term would be the relative entropy, or the entropy of a conditional probability of X conditional on no, I mean Y conditional on X, right?
Yeah, you can think about that way. Exactly. Yeah, it's actually that's also a way to present it. Yeah, that's good.
Sorry, which slides are we on?
It's slide 9. Slide 9. So that made us very excited. So we can do that. Of course, sorry. Of course, I'm not a social. I'm not doing social study, right? I'm not. Actually, I had a friend. He studied forest. He studied ecosystem, and that's actually why about 2019 we wrote this paper, discuss this one. We were going to apply to forest. I will show you a little bit later the significance of this equation. Okay, so this is we call the nested formula. So you can go all the way to quantum scale, then to whatever scale you want to go up. So that's what we found is so exciting about it. Okay, so any other comments, questions? If it's not, I move to slide 10.
What if we?
Yeah, go ahead.
Yeah, actually,
What
can
if
you
we?
can
What
you
if we start from the very the bottom layer of
Yeah.
refinement, at the very then your term will be simplified to the original ones, right?
Yeah, then it just has first term. I will show that one. I show that on next slide.
can you actually explain again the addition of the two?
Okay.
Yes.
So
Thank
so
you.
when you talk about the different states, right? So what I think about is that, for example, we talk about the room, okay? Talk about the room. So this room is the system, right? As a system. We have many chairs, okay? How do we arrange the chairs? Okay, that's PK log PK. How many ways to arrange it? Each way has probability. Or you can say in the room we have 10 chairs, we have 10 people, right? How 10 people arrange on those chairs? So that's the probability there.
Okay.
But then each person has entropy, right?
Yes.
So the total entropy would be the arrangement, given way to arrange the people on the chairs, and each person has a probability, has entropy too. So the entropy of the room would be the way to arrange the people, the first black term, and then each person at this kind of configurations and different entropy because not each person, sorry. So each configuration, because when you go to class, you like to sit together with your friend, so you get a kind of interactions different. So each arrangement of people in the 10 chairs will have different entropy for that arrangement.
I see. Okay, I sort of get it. But like the two terms, I think it's related something to what Hansen said. So the two
PK
terms.
PK is the same, right?
Yes, but like the two case, I know, PK is the same. But like the two sum, are they complete? They are not completely independent or something. How do I
Exactly,
say?
very interesting. So I'll show you the next slide how you calculate PK. PK is related to SK. PK is a function of SK. I don't have the equation there, but the PK is related to SK. Okay. The next slide actually is the next slide. Let me show you the next slide. Okay. Let's go to slide 10. It's total energy and harmonized energy. Total is like internal energy, harmonized is free energy. Okay. If you look at the classical statistical mechanics, that's by Gibbs, as in the 1870s. And that's what so in that case, it was the entropy of the system is equal to KB pk log pk. That he did an arrangement, okay? And then he derived the partition function. Partition function is z equal to exponential of minus f divided kbt. Kb is Boltzmann constant. And then because the system has different configurations, right? So your summation of all possible configuration. Now here's the total energy, internal energy of that configuration. So now you see, actually, it's funny, right? This is F, and in the middle is F, Hermann's energy, but on the right is EK divided by KBD, the total energy. So actually, it's some kind of a funny thing here, right? They're not the same. So if you take the equation I just mentioned, kind of Zentropy theory, and on the right side of the slide 10, you have now the purple, the blue one is peak SK minus KB peak log PK. If you go through the same mathematics, the partition point is different. So
sorry,
yes,
Professor Liu. Just quickly again, I remember the important of the original Boltzmann formula. He referred to the capital omega. That's the number of microstates. It's actually the direct counting of all the the finest.
That's right.
So if we are doing at a more abstracted level, say one level above, say you can think of FEA. I mean finite element type. You cross screening, and then you get less refined. Then on each level, the number of states, the counting will be incorrect. I mean,
it's different. It's different.
It's different, yeah. And I thought it's supposed to be at the most bottom level.
That's actually you're right here. That's the last line on slide 10. These two are equivalent when SQ equals 0. So when does SQ equal 0? It's for pure quantum state. So if your microstate is a pure quantum state, then SQ equals 0 because you only have one state. Log of 1 equals 0.
There's no variability at that point. It's just one state.
That's right. That's pure quantum state. However, the pure quantum state actually has a very interesting definition, right? What is pure quantum state? It's one state. Okay, that's first one. And it's at 0 Kelvin, right? Okay. Now, if the pure quantum state is at high temperature, what happens? That's the first question. Okay. The second question is that when people apply the equation, the original one, nobody started with pure quantum state. Do you know why they cannot do pure quantum state?
Tell us.
Because that means you will solve Schrödinger equation. That's basically Schrödinger equation is about. Schrödinger equation is about all kinds of states you have, all interactions. So basically, if you want to apply the left equation, it's okay, that's fine. So you have to start with the pure quantum state. Then you basically have to solve the quantum mechanics equations, Schrödinger equation. But of course, we know we cannot solve Schrödinger equation. But we can solve one simplified Schrödinger equation. I guess some of you know that equation we solve, right? As theory. Do you know what theory we use to solve Schrödinger equation today?
Well, I mean, that depends on the how many particles you have. If you say do like you can always start with the original equation, Schrödinger equation, and then compute everything, and or if you deal with the molecule, then you have density function theory, and then you can always and if you do the nuclear physics, then you have shell theory.
Yeah.
Exactly.
Absolutely. That's great. Thank you. That's exactly the point. So today, if you want to solve any real material, even not real, if you want to solve beyond the hydrogen, okay, so you have this density function theory to do that. Okay, so now as soon as I start to density function theory, you don't have pure quantum state anymore.
Well, I think what level you are trying to compute the entropy. I mean, in theory, it I mean, well, for first principle, you can always compute the entropy from the most basic particles, even from
Yeah, for
quark.
electrons, right? For electron density
Yeah,
states of electrons.
right. Electron or even from quarks, from the very constituent of the nucleus and
That's right.
the yeah. So, but let's say the thing is, if you do not, there's no change in the process. Let's say the initial stage and then final stage. If there's no change, the entropy. Well, actually, the absolute. I don't think we compute the absolute value of the entropy. It's
Oh,
the
that's an excellent
difference.
point. That's an
Yeah,
excellent point.
it's the
I think,
difference.
yeah, you made an excellent point here. Okay, so now, so what is density function theory? Density functional theory states that at a ground state, at 0 Kelvin, okay, at 0 Kelvin, there is one ground state. That's a pure quantum state. Okay, so for that pure quantum state, there's one specific electron distribution called electron density. So basically what it means is that in it, because you cannot track individual electrons, okay, so we can say, okay, but we have an electron distribution in the system. We call it density, electron density. But we know the theory is that there must be one electron density distribution, and it gives the ground state. There's only one ground state. That's what density function theory is about. Okay, that's very good. So that means now we're going to calculate that one. That's the distribution of electron. Okay, we got the ground state, right? Okay, that's fine. However, as soon as you start the temperature, as soon as the temperature is not 0 Kelvin, what happens? You have two contributions now. The electron densities will be different. So you get electron structure. You get the Fermi-Dirac distribution for electrons. Okay. Second, you got a phonon. What is phonon? Phonon is the atomic vibration. So you get the two distributions. Okay. Of course, you have two serial for that. You have the Fermi-Dirac distribution for electrons because the Pauli principle, and then you have the Bose-Einstein statistics for the phonons because they are indistinguishable particles. So from density function theory at a finite temperature, what do you get? You get SK. For each state, for each configuration, you got a SK. SK is a function of temperature. So now you see that as soon as you go beyond 0 Kelvin, you get so many quantum states mixed into one state. So if you can do DFT calculations for all of them, okay, and then you have the thermal electronic contribution if it's conductor. Of course, if it is insulator, you don't have electronic contribution because the electron, the Fermi level is 0. And then you have, but you still have phonon. Okay, so that what goes to the SK in this slide 10.
Professor Liu, I think this is a very key point. Would you be kind enough to repeat what you just stated about the definition of the
That's a really key part. Absolutely.
SK? Yeah.
So
appreciate it.
Yeah. So the SK here has. If we start I think it was Erica, right? Someone mentioned it was Erica, right? Yeah. Somebody was not. So as today's theory, okay, if you just go to theoretical part, go to Schrodinger equation, the left side is perfectly okay, but you cannot solve it. There are too many states. Okay. Based on density functional theory, to solve the Schrodinger equation, we have to have SK on the right side. Unless you set 0 Kelvin. Okay. As you said 0 Kelvin. Of course, at 0 Kelvin, you don't need a partition function, right? That doesn't matter. So that's really the slide 11. That's what we're talking about here. Yes.
So is SK defined similarly as before? Basically, also prior to that
actually, that's
definition,
exactly. So
you need to microstates need to be
that's right.
specified.
That's right. But in SK, when we calculate SK, we just need to pick log pk equation. Not exactly, because for SK, we need two distributions. One is the Fermi Dirac distribution for electrons. That's given by electron density, right? Electron structure. And then we need a phonon. So with both Einstein statistics for phonons. So SK has two contributions: electronic contribution and a phonon contribution. So both of them are pure states. So the individual SK is zero. That's the beauty of it. That's the beauty of density function theory, basically, really.
Well, they are together, right? Because
that's right. They put together. SK equals summation of these two.
That, I mean, the two phonon and electron, they actually exchange energy. I mean, at the key point, I guess the key question is how they reach the equilibrium temperature.
So
at KT.
Then that's a good point. Yeah, good question. So what happens is that, if you just do DFT calculation, you get 0K energy, right? You get electron distribution, okay? You have density, sorry. And then you have to go to finite temperature. As soon as you go to finite temperature, you're going to have the partition function as you show on the slide 10 here. Z equal to summation of EK divided KBT. Okay, when you do that one, so you calculate EK by the density function theory for all the electronic configuration, for all the phonon contribution.
I see. So the SK I can think of as subsystems, like composing the whole system, as, for example, the electron component versus phonon component.
Exactly. And it's beauty, right? Both of them use the partition function on the left side because they're pure states, pure quantum state. You cannot divide the phonon even further. At least in the quantum mechanics theory. Okay. So we're leaving the quantum mechanics theory. The phonon and the electron are both pure quantum states. So that's the beauty of the left equation works for it. Works for both. So the left side calculate SK, put it this way. All right. And then we add on top of that, we'll put a PK log PK.
But in Boltzmann's I think language, he would actually treat them as equal. I don't know. I mean, this.
That's right. So Boltzmann treated PK equal to 1 over omega. That's right. But in principle, it's incorrect because we know if you do quantum mechanical calculations, they're not the same energy. So PK is different.
So basically, it's the basically you do the maximization of the Boltzmann the Gibbs free energy with respect to the probability, and because of the convexity of the function. Of course, I mean that basically it's when you hold the energy constant, then you basically get the maximization condition gives you the Boltzmann distribution.
That's right.
I mean,
exactly.
Gibbs distribution.
Exactly. No, it's maximize entropy, minimize the free energy, right?
Yeah.
So get the same result. You can minimize the free energy on the F. Okay. You minimize F, you got the PK. Or you maximize S, you get PK. Same thing. They get the same results. Okay, and that's fantastic discussing. I like it.
So the thing is, I suppose you're gonna do the optimization at different levels, right? Each system and each subsystem.
Yeah, that's right. That's right.
Yeah. Otherwise, if you do well, the thing is, I mean, it should be consistent with the if you maximize the whole thing, as one ensemble, and as opposed to if you just set each subsystem as a closed system and then maximize or minimize the free energy in each for each subsystem, right?
That's actually an extremely important question I asked here. Okay, the first equation, S, is independent of an ensemble. Okay, ensemble only affects what free energy you use. So, for example, if you take the MVT, right, canonical ensemble, use F. If you take a Gibbs ensemble, use G here. So only difference is this partition function. The entropy itself is not affected. Same formula.
Yeah, I have a question here. It seems to me like you define this one is very weird because like the two components they mix up, you know, like one macroscopic pack is mixed up with the one level below it, the microscopic pack,
Absolutely.
and
You are,
and you know, like why don't you like treat them separately? Why do you sum them up in the first place, you know? And then, you know, if you go down further, you know, it's the effect of the each contribution, you know, how do you what's the usefulness of that approach, you know?
let me tell you that one. So that's actually a good question. If you go back to slide 9, you see that importance here. Because it's practically useful. Actually, next slide, not slide 11 too, but let's talk about slide 9. It's practically useful. When you do experiments, right? Suppose do X-ray, for example. You have a resolution. You have two resolutions when you do experiments. You have the time resolution and the space resolution. Okay. So when you talk about your results from your measurements, you actually define the scale already. Okay. So for example, if you use X-ray to measure magnetic properties, you cannot differentiate individual spin. You measure the system spin, the macroscopic, instead of microscopic. So it's really because of the experiments we do. Because in any experiment, we don't measure all the scales simultaneously. We measure one scale. All experiments one scale. And all the other scales, it's summed up as the data you have. So you don't measure individual scales at each measurement. So that's why I divided them. For example, if you do neutron scattering, if you do the synchrotron, okay, then you measure different scale. Then you need to have different the equation here. You need to do two different scales and line up. Actually, you guys asked just so many good questions. For example, I don't know how many of you know ferroelectric, lead titanate. Lead titanate at low temperature is tetragonal, polarized tetragonal. At high temperature, cubic. That's by X-ray. However, if you do another measurement with much finer time and space resolution, at all temperatures, they are cubic. They're tetragonal. There's no cubic. Okay. So it's really the homogenization by experiments become very important.
Yeah.
All
So
right.
basically,
Yeah.
if I so basically
Yeah.
you're looking at the different or scale or level where the lower level is not perturbed, not interacting with the higher level, and so
Exactly.
you're just just change the higher level configuration, and then the lower level is not interacting with the.
No, they are interacting. No, they are interacting. No, they are interacting. But it's your resolution cannot see it.
Well,
you see the average behavior.
The saying, well,
for example, let's go to slide 10 again. Go to slide 10, right? The left equation is correct if you start with the pure quantum state. That means if your experiment can sample all the pure quantum state, the left equation is correct. However, if your experiment cannot sample each pure quantum state, then the left equation is incorrect. You have to use the right side equation.
Yeah, but the thing is, if you have pure quantum state is changed during the process.
No, it's not. Pure quantum doesn't change.
No,
The
no, no.
electron
I'm
state
saying
doesn't
that
change.
if it is changed, let's say, I mean, I can make a, let's say, photon, a very high energy photon, and it destroy or it excite the state in the lower level, then there's an interaction, right? So the state changes, then I have to compute that entropy. I mean, compute that state,
Absolutely.
count
You are right.
that state
Yeah.
into the
You're
computation.
right. Yeah, you're right. For example, because you see the left equation is the base state is pure quantum state. If you say you go below the pure quantum state, right? Then that most is actually. You're right. Yeah.
Yeah. So
You're
this
absolutely right.
is
You can do.
okay. Yeah.
Yeah.
So this is basically, yeah. It's looking at the most to make it more efficient in calculation, right? Which are not those which are not changed, you don't uh, uh, account for it, because the final result matters only only the change in the entropy matters, and not the absolute value of the entropy, right? So whichever level that is changed, you account for it, and then within like at a smaller scale, smaller resolution or higher resolution, if it is not changed, why do you want to account for it, right? So just um, only you investigate on when it is needed, when if there's any change in the finer scale, right?
You can think about it that way, but if you take the left equation, you take the same state to calculate, you get wrong results. Okay, that's actually next slide. That's the last slide 11. Okay, so you do experiments, you measure thermodynamics, you can measure heat capacity. You can measure it. You measure heat capacity, you do integration, you get entropy. You have to put the two together to get the right entropy compared with the experiment. If you don't do it, you cannot. That's why in the literature, nobody can predict the heat capacity for this kind of system. So you take each part of it. So you see, the red part is the quantum mechanics. If you take quantum mechanics alone, you cannot the result will not agree with the experiment. If you take the blue statistical mechanics alone, you cannot agree with the experiment.
It seems like seems like really like you said at the beginning, like multi-level.
Yeah,
so
right.
so the macroscopic one, the entropy, it doesn't automatically contain completely the lower scale, right? So that's
Absolutely.
why you have to take into account the lower scale when necessary. That's basically
Yeah,
that's
you're
what you are
right.
saying. That's the
Exactly.
okay.
Yeah, necessary. What's defined as necessary is when it's changed. If it is changed, then you have to take into account. You have to investigate and take account for it. If it is not changed,
But
then
there's no
leave it
case.
alone.
But there's no case you can take the blue term the blue term only agree with the experiment. It doesn't happen.
So
The reason is because
So did you
always
apply?
have the red term here.
Did you apply this to some real experiment? Did you check?
Oh, of course, we have many of them. Okay, I've showed. I talk about some expansion and the quantum criticality. That's actually next the slide. No, I want one more slide. Slide 12 before I go to the results. So now we need to make it more general about entropy production. Okay, entropy production. Now I divide them into 4 terms. The first one we typically talk about is the heat, the red one. But as a human, right? Human is a system, or any actually organisms. You have to consume something. Okay, then you produce something, then you produce information. Okay, so the heat generated, the nutrient consumed, waste generated, and the information destroyed. So that's the total entropy production of any process. Now we can apply this one to the cases. Okay, this is one. I want to show you one example. The cerium. Cerium is one metal. So now it says this is phase diagram. If you have heard before, water is phase diagram, temperature, pressure. You can change the volume to pressure. That's just like a temperature pressure phase diagram. But if we want to do the volume, some expansion. So now what happens is that in water, water and the vapor has a critical point, right? Okay. So that's critical point here. Same thing. At the critical point, volume expansion, V to T derivative, diverges. That's the definition of a critical point. The system becomes unstable. When it's unstable, T to V goes to 0, V to T goes to infinite derivative. So all the lines are prediction from our model. And the dots here, the symbols here are our experiments. This is without any fitting parameter. Just use the equation I talked about. Calculate DFT with the quantum mechanics calculated and the statistical mechanics put them together. We predict the critical point. I will challenge you if you tell me anybody has predicted the critical point in the literature without any fitting parameter. This is magnetic transition for critical temperature. That's fine, right? The volume expansion. But I want to give you another dramatic one. It's on the right side of the diagram. So this temperature volume. So each line, each curve here is for fixed pressure. So this is the one is you see the one with zero pressure. That means ambient pressure. Okay. Now, if you look at the right diagram for iron strip platinum, iron strip platinum is the INVA alloy. INVA alloy was discovered about 1890 something by a Swiss scientist. He got Nobel Prize because he discovered it. So in that alloy, he discovered is iron nickel around. The some expansion becomes negative. Some negative is not a phase is not a two phase, it's still a single phase. Okay, you see this one on the iron 3 platinum, you have these black dots. When temperature goes up, volume first increase, and then increase less. And then with the proper the symbol range, it becomes 0. Then decrease volume, temperature goes up, and then decrease less, then becomes 0, then increase again. If you increase the pressure, and the line moves to the left, and reach the critical point, that's the volume negatively diverges. Okay. So that's completely predicted by our theory, about the Zentropy theory. And again, there's no fitting parameter. Take the DFT calculation for number of states. I will give you so surprised, right? For the cerium, we only have 3 microstates: non-magnetic, ferromagnetic, and antiferromagnetic. That's different spin configuration. For iron 3 platinum, we have 512 states, different spin configurations. So this is application. Again, the symbols are all from experiments, and the lines are purple symbols are from predictions. All right, that's all I have. Wow, I think 1 hour. That's good.
That was great.
Excellent talk. I had a question.
Now, I want to mention one more thing. Okay.
Okay.
So that's why I think this can apply to society, right? Society is kind of homogeneous. But when that society becomes unstable for the good reason, unstable for the bad reason, but for the bad result. And if I consider the positive, but it is bad, right, so to speak. You get a huge expansion of the volume of society, or huge contraction. So contraction means that society destroyed. Expands that society expand to conquer other places. So it's a critical word. It's an instability of society. That's why I think it can apply to society too. Big Bang is instability, right? Or the black hole is instability. That's actually what
the
they
collapse
see.
of civilizations due to these dynamics that you just described.
Yeah, exactly. And actually, you see, if you have listened to you read the book by Stephen Hawking, his focus point of his theory is singularity. The critical point here is a singularity. All right, singularity. That's the end of the story. Thanks everyone.
Yeah, thank you so much. That's great presentation. But please go ahead and ask your questions. Tuan, Dr. Shah, you didn't get the chance to ask a question. Please go ahead.
Well, okay. So this, some of this reminds me of some work. Well, molecular dynamics is very much approximate, but getting into a deeper understanding of hydrogen bonds. I remember a science paper, and in an electronic structure, we'll make a Born-Oppenheimer approximations, which says that while the nuclear motion is so slow, the electronic configuration can just adjust to it. And so we can separate those two calculations and ignore the coupling. But in terms of a particularly interesting science paper on experimental paper on the hydrogen bonds in proteins, it was shown that the the hydrogen on the donor going to the acceptor will end up tunneling back and forth and will have a resonance time of somewhere around 10 vibrations within the acceptor donor pair. And it struck me as how inaccessible our present theories our methods of calculation are to really get to the energetics. And as I'm listening to your talk, it seems like there might be um, a novel approach to the accounting and the energetics there. You have any comments on that?
Yeah, it's absolutely. I fully agree with you. So you see, all the work we do now today, most of the work, okay, is that we cannot predict. We cannot. You see, there's no closed mathematical form for singularity, right? Because you have to go through singularity to other side. So you cannot have one mathematical equations go through. You cannot have one Hamiltonian to go through the singularity. Diverges. Okay? So that's the fundamental problem we have, all the mathematical representation. So in this case, we have here, in principle, if you want to get a very, very sharp singularity, you have to have an infinite number of states, right? Configurations. So that's got the, because that's what they say, with the singularity, your wavelength becomes infinite, basically. Fluctuates everywhere. Okay? But in the reality, of course, when you approach that singularity, it's not an infinity yet. So our approach basically say, okay, when you approach that point, you can see that it starts to diverge. Okay. So if you want to make it a very sharp diverge, then you can actually predict it. So any Hamiltonian approach has a limitation. You cannot do that. So that's what I said. There are two parts of our equation. The first part, for individual well-defined configurations, you can calculate them use density function theory, is quantum mechanics, well-defined. So the singularity really comes originates from the competition of different microstates configurations. That competition is represented by the second part of the equation. So you have to have both equations together, both parts together in one equation to predict singularity. Otherwise, all the theory can describe a singularity. You can say, okay, I'm going to describe it, use this formula, right? Then you say the divergence there, but you cannot predict it. I hope that answers your question.
Yes, thank you.
Dr. Liu, I had
So
a few questions. One, we're a little bit past the top of the hour, so just wanted to check in with you, see how much time we have left with you. And number two was, what drew you to science? What was the first thing, or how did you end up a scientist?
Okay, that's a very good question. Thank you. I like to talk, so I think I can talk another half hour, 1 hour if that's necessary. All right, but I have to do housework after that too. Okay, that's good. Okay, so I grew up in a mountain area in China, remote mountain area. I was told the grown-ups told me when I was young. I always ask people question why this, why that, why this, why that. I don't know why I do that. So I have this curiosity. I want to understand why things work, how things work. That really pushes me. So in China we had a cultural revolution when I grew up. So I didn't have much education, so to speak. So the university in China were closed from 1963 to 1973, 10 years. There was no university basically. Okay. So in 1976, they started to see, oh, maybe we should do something now. And in 1977, they said, okay, let's open university again. Let's open universities again. So I was first in high school at that time, and then my principal, and university principal, the high school the school principal, he said, maybe Zi-Kui, you want to try to take the exam to go to college. I said, okay, I didn't know. So they said, okay, let's do that. So I didn't finish high school, so I went to take the exam, and I passed the exam. So I get to college before I finished my high school. Of course, that's abnormal, right? Because that's just the time history. And then when I finished my college, 4 years, I like to ask question again at that time. I like thermodynamics. Okay, the thermodynamics was my favorite class. But I have to tell you that the teacher was pretty bad at that time, and his teachings like made everybody sleep in the class. Anyway, so I really like thermodynamics. I took that one, and then when I finished college, I need to decide what to do. Right at that time, again, they started open grad school. Okay. Grad school actually also started in 1977, 78, but very few people can get in. And then my father said I should get a job. He actually gave me a job to work on, but I said no. I want to study more. I understand more. So then I took the exam. I got the grad school. Again, the reason I got into grad school because I did well in thermodynamics exam. And then I met my wife. I got married. She was my classmate. And then I continued to get my master's degree. Then my wife went to Sweden. I followed her to Sweden and get a PhD. I always like to talk with people, talk with ideas, ask why. Then I said I had to become professor because that's where I can really freely ask questions and teach people about knowledge too. I've been in Penn State about 23 years now.
Professional asking the question why. Yes, that's one of my favorite questions.
Yeah. I really like that. Always. So when my students here, I graduated students, right? So I told the students, you have to ask 3 whys for one question, or one issue, right? If you can answer all 3 whys, then nobody can ask you question anymore.
What are those 3 whys?
Now, 3 whys is that, for example, why do you do this, right? You got some device, then you go with 3 levels, just multi-scale.
Multi-scale and nested.
Yeah, exactly. Nested 3 levels of question, whys.
My favorite question. Who else has questions? Flash your mics.
I have a question. So thank you so much. First of all, that was a very fascinating paper. My question is about the configuration because you just explained a couple of the, equations that you just used previously. So the configuration part, does it have a use in for the black hole? Configuration or not?
That's right. So if you, of course, again, I'm not a black hole expert, but very simple understanding of this one is that in Stephen Hawking, and actually before him, there was another a young person. So that's what I know. There are many young people here. The young people have a lot of ideas, right? So when they try to figure out the entropy of a black hole, they did a lot of mathematics, okay? But their conclusion was that the entropy of black hole is proportional to the area of the black hole. That's the final conclusion. So what does that mean? So what is on the area of the black hole, right? Think about this one. Okay, so is Shah, right? Was Shah you answer that question? Okay, Shah, what do you think? If you talk about the area, right? The entropy is proportional to the area. What does that mean?
Yes. What does it mean?
Yeah, right. So entropy we talk about the entropy is KP is P log is KP log omega, right? omega is
Yes,
the
it's
configuration,
solving
number
that
of configuration.
equation, right?
Yeah, but in their equation, the derived say entropy is proportional to the area of the black hole.
Actually, the area of the black hole, it doesn't mean that much. I mean, it doesn't have that much meaning to me because in a certain point, we're gonna have the infinite, you
Yeah,
know.
so that's right. So that's exactly right. So what it means is that you have a large area, you have more way to arrange your stuff. So you get more high entropy. So that's what the black, at least at the moment, the black hole entropy is like that. But I really like to do if I, since this news published, I know you guys found this one too. It's really that the nested form, right? Actually, I got an email from a cosmologist, and he said, "Oh, maybe he want to apply this one to the to the black hole." Actually, no, he want to apply this one to dark matter. He said this can be applied to dark matter. So
I
I'm
see,
waiting to see
Zi-Kui.
whether you
I
can.
think you answered my question, but I mean, in another part, I mean, I was just wondering about the producing the data because when we are thinking about the, I mean, quantum level, it's different, and when we are talking about the data producing with the matter that you just explained, that's a different level because even in the biology, in the system biology, even sometimes I think that it's possible to produce the database upon the equation that you just explained.
Yeah. So in the biosystem, it's so complex, right? So it's really much bigger than the problem I'm addressing because in my case, I address atoms and I address the magnetic spins and the polarizations. If you go to in my opinion, if you want to truly predict the biosystem, you need to start from the quantum first. You calculate the molecules, then you calculate the molecule arrangement. Okay, so then you have these different configurations together. Then you talk about how the molecules we arrange them in the space. Then you have this at least 3 or 4 levels more than the one I present here. But I still think it's important thing, in my opinion, is you really have to you have to account all the entropies which plays a role in those biosystems. If you just take one level, like many people do, that's insufficient. It will not give you the predictive power you have.
Did you ever
Dr. Lee,
consider it? Did you ever consider it the full configuration?
Yeah, that's right. But you need to. But you see, but it's so complex. You cannot put all the configurations at different levels together. You have to separate them layer by layer, level by level. Then can do it. If you so see, that's why the original statistical mechanical equations cannot be used. People use it wrongly. Okay, they didn't use if you want to really use the original one, you have to do all the pure quantum state. That means you have to solve Schrodinger equation for everything. You cannot do it. It doesn't work. So people didn't use that one. They use the non-pure quantum state. They apply the equation. That's one implication of this state. So in this case, we say, okay, let's separate the different levels. So which level we can predict, we can calculate, then put them, then stack them up, basically. So I think it's the same for the biosystem. You have to stack them up at the different scales. Then you can truly predict the performance or the properties of a molecule or of a organism.
So if we compute the Gibbs distribution, um, which is as we discussed before, which is the maximization of entropy or minimization of free energy. If we look at the distribution, computer distribution at certain level, which would be let's say a um, coarser demarcation of the states. So basically, you have the coarser demarcation, say the subsets of the state space, and
Yep.
so if we do the same thing for maximizing the free energy, maximizing the entropy or minimizing free energy, we should get the consistent distribution. And I think the demarcation or the selection of the subsets, there should be a condition on the selection of the subsets, right? Or in other words, in physically speaking, how we define a level as opposed to another level. I suppose we cannot just arbitrarily select the subsets or the arbitrarily demarcate the levels, different levels, and then just do the maximization and minimization in that level. Is that correct? There
Okay,
needs
so
to be
that's a great question.
definition of the
That's a
levels,
good
right?
question. Okay, yeah, that's a good question. But I think it doesn't matter, in my opinion. Let me explain why it doesn't matter. Okay, so if you look at the slide 10, right? Let's see, I think it's slide 10. Just make sure I get the right slide there. If you look at the slide, slides 11. Slides 11. That's fine. Oh no, slides 10. That's right, slides 10. So if you can access all the pure quantum state, you can get all the properties of them. Then you can use left side equation, right? Okay. So now the right side equation is basically the assemble the high level of the left side equation. Okay. So you put them some together. So what does it mean? That means, so basically from left side to right side, there are infinite number of ways to combine them. You combine any way you want if you can get the data.
Yeah,
So
I agree. I agree with the first equation, how you compute, given the probability of states, this is always true. It's just the getting the entropy of let's say two random variables from single one of them, and then combined with the conditional entropy. And this is always true given the probability. What I'm kind of concerned about is the second line for the distribution, because the distribution comes from the maximization and or minimization, whatever optimization you do to get the distribution. So if you take we can always
I have the answer for you. I know your question. I have the answer for you. Let's see.
Okay.
Let me give you an answer, see if it's correct. Okay. So you want to use the right side equation, right? So each k, that state, must fill the whole system. That microstate cannot be part of the system. It has to fill the whole system.
Which slides are we? Which equation are we?
It's slide 10.
Okay. And
okay.
which equation?
So that SK, right? And SK is very important here. And SK, because that SK represents one microstate, right?
Yeah.
That microstate is not a pure quantum state. That microstate must fill the whole space of the system.
So basically, the microstate has to be interacting with the whole system, right? The rest of the system.
Right? How do you interact with the surroundings? Yes, right. How do you interact with the surroundings? So I have to experience the same constraints as the whole system.
Yeah. So
that's exactly what you mentioned. Because if you take a microstate that is not experience the constraint for the surrounding, the right equation is incorrect.
Yeah. So then I'm just trying to understand the meaning of the the Z on the right-hand side,
Yeah.
especially the summation in the summation notation. On the
Yeah.
exponent, you have fk, right?
Yeah.
So, and I suppose the fk. So if you're interacting with the rest of the rest of the environment, the rest of the system, which is in called environment, then the fk. So okay, so of course you can make the fk as a kind of a variable, right? Depending on what the environment gives you, um, and yeah. So if it is um, the it is given by the environment or computed from the environment, yes, you can always make the everything consistent. But my motivation of the question is, I'm trying to see if if I can make everything consistent, because it seems to me that you're trying to basically at do this because to make the computation convenient, we do not need to compute the whole system, but just the part that we need, the level that we need. And I'm trying to see that, or prove that under what condition that we can isolate that level and do the maximization and or minimization within that system without bothering the environment or the rest of the system. Or of course we can use a few parameters to represent the environment or the heat bath. Um, so I don't know which approach you're taking, the one or two parameters to represent the heat bath, or making this completely the level completely closed.
Okay. So what it means is that when you talk about the interaction with the surroundings, is basically the ensembles, right?
Yes.
So, so as soon as you fix the ensemble, you fix the free energy. So that's really just to go back. So if, for example, if you do the MVT, you get a harmonic energy. If you go to the MPT, you got a Gibbs energy. If you fix other variables, you get different energy functions.
Yeah, yeah, yeah. No,
Hanson, Hanson. So I think like the thing is, statistical mechanics as taught in textbook is still correct, because like all the formula you see that they apply to ideal gas system, like they are able to reproduce, the ideal gas equation and things like that from the quantum distribution. But I think in the case of what Dr. Lee showed today, he showed that for some system, for some real system, where you do measurement and things like that, you don't see, the experimental data, agree with the theoretical calculation unless, unless you add, more stuff, right? And so that's why his formula comes in. So I think that eventually the question is really about, whether or not his formula applies, correctly to experimental data, right? Is it like that's the?
no. I'm saying that the formula, the statistical mechanics is correct, and the maximization, basically the distribution comes from, of course, I mean it's the equilibrium state, and then we're not talking about the non-equilibrium state, right? And then equilibrium state, and then so basically you look at the whole ensemble, and then if you optimize the system, you get the distribution. So the thing is, in principle, we're done. The job is done. But let's say if we trying to, if we're trying to make the computation more convenient and faster, right? So some of the computation we don't need to deal with the whole system. That's what I think the motivation of this research is about.
No, you
So
still deal with whole system. No, you still deal with whole system. You still do so because you still have the stuff on the quantum state. Okay.
Do you
But the only thing is,
consider
but the only difference is that you put those pure quantum state, add them together as one macro state. That's the
yeah
only difference.
so but
So that's a
Well,
little
there's still some practical issues in computation. Even when let's just go back. Okay, we'll start at 0 Kelvin and we'll start to heat something up.
yeah.
I mean, if you get a system, well, to handle the electrostatics at a larger scale, you like to employ periodic boundary conditions. But we're not going to be able to, some of the finer details are going to be aliased in when we go in and out of frequency space for that. And so we're not going to be able to capture all the terms that we need, right? We're
No,
going to
you
be
do
missing
catch. You
things.
you catch all the frequencies. You catch all the phonon frequencies. You capture all the electron frequencies too, but
But we have to impose the periodic boundary.
That's right.
So,
That's right. Oh, you don't have to do that because you can do the molecules, right? You can Gaussian distribution. You can do the single molecules too.
well, for a patch of material, as you scale up, I mean, say, let's go up to 100,000 atoms or so.
Of course, then you cannot do it. Of course, that's beyond your scale. That's right. That's right.
Right,
You have
right.
too many states. That's
But
right.
even if you're down to a smaller patch where you say, okay, you got your exascale project funded and you're going to go
That's
compute
right.
these things,
That's right.
but you're still the long range electrostatic. You still have to apply these periodic boundary conditions, and so, well, yeah, you're stuck equilibrium, and you can't study heat traveling. You can't have asymmetric boundaries if you're going to go periodic. So you're
Yeah, I agree with you because the density function theory. When you want to make calculations, you take the periodic boundary condition. That's right. That's right.
so we won't have all the right states to add up to even apply your formula to. We
Yeah,
wouldn't.
but I see, the most of the problems we have, right? Most of the problems we have, first, they are relatively short range interaction. That's one thing. And if you do have very long interaction, like you just mentioned, electrostatic interaction, very long range, is way beyond the supercell we do, right? But it turned out we have a solution for that too. So what you do is that you don't do it in the real space, you do it in the reciprocal space. That's the beauty of it. We have actually a paper on that, a few of them. So what do we do? Let me tell you, see if you see that solve partially of the problem. So in the real space, you do the periodic boundary condition. You know it's incorrect because the long-range electrostatic interaction is not considered. And then you do that calculation. Okay, so how do you want to how can you consider this long-range interaction? So what you do is that you go to reciprocal space. Now this becomes very interesting now. Why is it interesting? Because the infinity distance becomes the origin, the 0 point. That solution is analytical. Okay, so now you can take the analytical equation, like the solution you have, you can add on top of your real space periodic boundary condition. And of course, then you still have a problem, right? So what is the super between the superset and infinity? Okay, then you do some interpolation. It actually worked out pretty good.
What I find uh, confused about this, not confused, but like when I look at this formula, I feel it's a little bit strange because it's not based on any theoretical foundation, right? Like it's almost
Which one?
like
I mean, this one you mean the Zentropy?
yeah, the Zentropy, like your definition.
Oh, it is. It's exactly okay. You look at this
Like
entropy, right? That's exactly on our slides. You look at the slides, start slide 7.
yes.
Okay, you first start 7. That's exactly fundamental. You start. It's purely theoretical revision. No assumption here. You start with the system entropy. You say, okay, system has different microstates. This microstate is important. It's very important. As I think it was Hansen said that once. Right? It's very important. Each microstate here has to experience the same constraints from the environment as the system. That's why you can apply this peak log pk. Okay. So now The next thing is that, okay, this is only part of
Yes,
the entropy of the
yeah,
system.
but like the addition part is, it seems to me it's very heuristic, like it's not.
Oh, no, no, wait. Are you
Is
saying that?
is
Sorry, Troy. Are you talking about the page, the
8. Go to page
equation,
7 or 8.
page
7, 8, and
8?
9, right? 3 pages.
Yeah, it's 3 page. The equation. So you're saying that the plus sign, the blue, black summation plus blue summation is strange?
what I'm saying is, is a heuristic
Oh, no,
formula,
it's not.
is
It's not. It's the so basically the two sums. So basically you have a the blue so wait the black one, the black one is kind of a coarser level, uh, the entropy, and then the blue one is a finer level
yes, but like
entropy.
there's no principle to say that you
Oh,
have to
yes, there
add
is
them up,
principle. Okay, yes, I can prove it to you. I mean, this is, oh, you can just look up the Wikipedia information theory, the entropy. So the relative entropy formula that the entropy of xy is equal to entropy of x plus the entropy of y relative to x.
So Dr. Lee, so are you saying that your formula, the addition, it is, coming from first principle? It's not a heuristic formula. Is it a heuristic formula, or is it, did you derive it from first principle? Some first principle. Like, what are you saying?
Um,
Is it a heuristic
I
formula, or is it, did you deduce it from some first principle? That's what I'm concerned. Because if you, deduce this, if you, derive it heuristically, it means that, that you will eventually, you will see system where it's not applicable anymore, right? Or you will come to situation where, your formula is not correct anymore. You see what I mean? Like, it's not theoretically based, and so you don't understand exactly, the conditions that, that will make your formula correct. Like, you don't have a complete understanding of that. Is it true?
I don't agree with that. I think one thing here, this one equation looks like it's discrete, right? But it's not discrete in principle. It's actually continuous. Continuous means that you can think about at any given condition, what kind of states that a system could have. You can do as many as you want. You can infinite number of configurations possible. Okay, then you get a first term. They're going to range them in space based on probability. And then each state, it's just like the first law. It's like first law. Okay, first law is energy conservation. This one is about entropy, a combination of the system. It's how you can divide the system into all possible configurations. You can imagine anything. You can imagine. Okay, then you get a first term, you get a second term.
Okay, I see. Okay, so you are saying that this is its status is like the status of the first law, where you cannot prove it or deduce it. You just have to, see that it's correct for many systems until it's proven wrong.
Agree.
That's
Agree.
that's what you are saying. Okay,
That's
okay.
exactly right.
Is it more that it's an accounting and grouping of states that are in your system?
That's right. Exactly. You can count as many as you want.
Well, so
That's true.
this is no, it's not the axiom. It is you can derive it from the definition of entropy, just the
That's
log
right. Exactly.
p log p, summation of negative p log p. It's just a matter of the conditional probability.
Yeah. Exactly.
Hanson, so you were suggesting a Wikipedia link. Which
Yeah,
one is it?
just
Is it
look
the
at
entropy?
yeah, because originally I wanted to write down the proof, but of course there's no way you guys can see what I'm writing down. But just looking at the let's see, hold
Okay, so
on.
you are saying that this formula it is derivable from the general formula of entropy. That's what you are
Yes,
saying.
So,
yes, yes,
Okay.
so
yes.
Hansen, let me check. I got you what you're saying correctly. So you're saying the page number 9, the equation, the right side, the first one is the p's are conditional probability, while the blue ones are the real finer. But the question is, how do you get the
Let me
sk?
hold on.
That
Let me see which one is which because I
uh,
switched the
I should direct the
uh,
question to Professor. If that's correct, then the problem becomes the measuring or calculating the subsystem entropy, right? How do you do that?
Yeah, exactly. That's what we, in our case, we use the DFT.
I see.
so
So
basically yeah the on page 8 so the black one, the black summation is the let's say if we computing x and y, right? So that is the x entropy. I mean, random variable x and y. Let's say s. Uh, in general, I'm talking about this is the most general statement rather than the states and microstates and all that. So S, let's say S is a function of random variable X and Y. And then the black summation is the entropy of X, and the blue summation is the entropy of Y conditional on X.
So, like if you are saying that is derivable from the general formula of entropy, why is it being called Zentropy then? Like why don't just call it entropy? You know, normally why do you call it Zentropy? Like why?
That's on slide 10.
Okay.
I think Hansen, I mean, what Hansen just said is the opposite of what I understood. Maybe I got it reversed. So, which one is conditional on which? I thought so the S in Professor's formula is no different from the original one. It's just like a different grouping. That gives the,
No. This is the smaller system, the microsystem. SK is the the smaller within that smaller system. You have the entropy. Uh, but the PK is the bigger system. The
that's right. So that's the bigger system is the conditional probability, right? Conditioning
no.
on the micro.
Conditional probability is smaller. So the bigger one is the bottom. So X, so Y is conditional on X. So given X,
Okay,
you
okay.
look at
See,
Y. Yeah.
yeah,
So
yeah.
so
So yeah,
Y
which size?
conditional on
Okay.
X is
So,
smaller. Yeah.
yeah, so I think it's very interesting. I will look more
Actually,
into the
I
paper.
want to point out one paper, but Hansen just talking about Hansen. Let me share the one. I don't know where I can share. In one of the papers, I work with statistics. Exactly what Hansen talking about. Actually, the whole equation here is probability. It's a conditional probability. I think if you go to my website, if anybody goes to the website, go to my group website, and you look at the publication. Let's see what number is that. If you look at the publication, you go to the website. The number is let's see, let's see. It's number 488. 488. Number 488.
Thank you, Professor. Yeah, I will.
That
I will.
paper. My
Yeah.
second author of the paper is a statistician, and he actually explained to me about our approach exactly what Hansen just said.
Okay, so I will read the paper. Thanks, Professor. I have like since you are an expert in you know statistical mechanics, I would like to ask you one very general question about statistical mechanics, uh, and that is you know this question. So you know like people usually say that you know we do uh, thermodynamics, you know, because the number of you know possible microstate is too large, you know, right? So we have to take you know average, you know, to get from microscopic physics to macroscopic physics. But my question is, when you do the full, statistical mechanics, what will you get then? Like if you don't do, the averaging, will you still be able to get to macroscopic physics? Going completely from a microscopic physics.
That's what I believe Zentropy can do it. I think the existing statistical formula that's on the left side of slide 10, you cannot do it. The reason is because you cannot sample all the pure quantum state. So it's theoretically you can, but not in the practical. Okay. But with Zentropy we have, with DFT basically is one level of homogenization. Okay, it homogenizes electrons basically. If we take the DFT as our starting point, then the Zentropy can predict from the microscale to macroscale. That's my conclusion. That's why I'm so excited about it. I want to go back to the question Hansen about the probability. Is equation 9 in that paper? Hansen, you nailed it. I usually don't talk about that one because not many people are familiar with this one. If you look at the paper, the equation number 9.
Oh, wait. Which paper? Can you
So
repeat?
488 in my publication list.
Okay, I see your
Yeah.
website. I see your website.
Yeah, you go to my book website. Faces.psu.
I'll change it back to paper, the pin.
You go to my website, right? Faces.ps.edu.
Hold on. The MAT. Wait, directory. I got the Penn State College of Earth and Mineral Sciences, right? Department of Material Sciences.
Yeah.
Is that
you
the
go
page?
to Faces, right? It's my group faces.psu.edu.
Yeah, psu.edu. Yes. And then
that's my website.
Research.
You go to publication. You go to publications.
Hold on.
Then you go to number 488. You search 488.
Actually, I think I see a picture. There's graduate research. Oh, maybe that's the department website.
No, you go to Faces, right? Faces.psu.edu.
Faces.ps. Oh, SFCE.
Yeah, PH. No, PHASE. PHASE.
I just texted you the website link on the direct messages if you go on there.
Oh, hi, so you made my day. I never used this one much in my presentation. I will put this one in my future presentation.
Okay. Oh, I got the Phases PSU.
You go to publications. You go to number 488.
488.
You click the DOI number.
Okay, got it.
Then you go to number 9, equation number 9.
Okay, multi-scale entropy and its implications to critical phenomena emerging from evaluation. Okay.
Yeah.
Equation
9 is exactly talking about. It's about the conditional probability.
Right. Yes. Yeah. So equation 9. Yeah.
It actually, this guy, the statistician, he inversed my problem even, right? With from low scale to high scale, he said from high scale to low scale, same thing.
Yeah.
He proved that.
Yeah.
That's equation 13 and 15.
Yeah, actually, I think.
So then, what I said earlier is also correct. Is that okay? By the way, Hansen is our in-house physicist.
It's fantastic. Okay, it's fantastic. You guys are just wonderful.
I think Jake had one question. He texted me a while ago.
Okay.
If you have time for one more question, thank
Yeah, go
you.
ahead.
Hi there. Thanks for the room. I always appreciate it. I have a question. I'm, of course, not a professional in this at all. I was just curious if a black hole is really just a photon star, like a collection of photons, since photons don't have mass, but they do have gravity. Would it be possible for uh, a black hole to just kind of become a huge collection of photons?
I
My
think
understanding is it's the inverse of that potentially.
okay. If you ask, because again, I have to say I'm not a cosmologist. Okay, but
I have a question.
I can give you my understanding of it. How about that? Okay.
Wonderful.
So my understanding is like this, right? I in my new paper just published, I talk about the quantum criticality. Okay. So quantum criticality is so interesting. So if it basically says that you have 0 Kelvin, you have the critical point. Okay. So what happens is that if we approach that critical point, okay, and then you see divergency. If you go away from that critical point, you see the divergence disappears. Okay. So it could happen that we have Big Bang, we have black hole. So it's just the two sides of the one singularity. That would be my answer. I don't know. I really don't know more than that.
It's
I see.
actually really interesting in terms of astral imaging from all of the available space-borne observatories. There are only theoretical models, and there have been some, like there was one image recently, but it was very rough. So it's a little hard to describe right now beyond theory and equations.
That's
I
right.
have a
But I
question
do
about
I do believe that entropy has to have this multi-scale integration together. You want to talk about the entropy of black hole, unless we're talking the pure quantum state.
Dr. Z. I have a question about your. I came late here, but it seemed quite interesting, and I was just wondering. It would seem that one of the implications of what you have here would be also, and I'm wondering if you have any comments or thought about it, is a more it would be a more fundamental explanation of convection. Is that something you've looked into as a
No,
result?
I have not done that. I fully agree with you, because the reason because convection is a spontaneous process, right? It is the irreversible process, so to speak. And if you think about this continuous convection, okay, that means you have to put some energy into it. So you have to really define your ensemble. But I think many people, when they start that problem, they didn't define the ensemble to study. The reason is because they cannot fix completely the interaction between that system and the surrounding. That's a challenge, I think. I think that if you can define that one, then it should be applicable. All right, sounds very good. Katerina, do you have any more questions? We're done.
I think you've been talking almost 2 hours. Thank you so much for that. It was such a pleasure to have you, and you gave such a great presentation. We learned a lot from you, so thank you for sharing all your time.
Oh,
And
we got 129 people here, and I saw that.
yeah, we had a total of 129. And yeah, thanks for coming. Always come back anytime. I hope you will come back and maybe participate in rooms or come back and explain us some more. And yeah, thank you so much. I hope you enjoyed it.
Thank you. Oh, I always enjoy interaction. But for some other people, if you really want to start the process, internal processes, and they have one new paper is accepted for publication. That's 500. Wow, I like the numbers, right? I can see that. Okay. If you are interested to learn to discuss with me further. That's my 565 paper. 565.
Wow, that's amazing.
Number 565 on my publication list. And that paper, in my opinion, I started working on this one in 2014-15.
Oh wow, yeah.
So that paper is like 50 pages, include reference. I just went through the proof yesterday. I submitted the proof.
Oh, congratulations.
Yeah, so the DOI is not working now, but I do have a archive link working for that one. So that one, in my opinion, it's going to be. Somebody was asking about. I think it was Tuan asking about applications, right? That paper will show almost all the physical properties we measure can be predicted.
Yeah, please come back and present it. Let's email and arrange a time that you're available. That would be amazing to have a follow up. It's basically ongoing story then here.
That's right. Okay. All right. Thank you
I
very much.
really
Thank you for the opportunity.
Thank you.
really appreciate it, Professor Liu, and the very advanced research, and you explained it so well. And then, by the way, you mentioned. Thank you for mentioning the exact equation 9, which actually turns out to be what I said earlier. I mean, I guess I misunderstood what Hansen referred to. It's actually the summation of the macro, and then the P is actually conditionally on the. It's the big one conditioning on the small one. Is
Yeah.
that correct? I think
Exactly.
that's correct, right?
Yeah, it
So
is.
Hansen, I was right.
Actually, I don't agree.
No,
Actually,
you
the second term.
you
Just
want to look
look at the
down there, right?
equation.
Yes, we switched because the equation, the second term is the first term in the black term in the PPT, and so this is not the conditional. This is the lower the coarser level entropy, and then the SL slash vertical line K. That is the conditional entropy, and that is the
Maybe we
second term
should
or the blue term.
invite Professor Liu to a private
Hanson, is it too
special
like
seminar room. Yeah.
Well,
like
Professor, did your co-author prove they were equivalent?
Sorry?
Didn't you say your co-author proved they were equivalent?
Yeah. That actually, if you look down there, there's equation 9, right? The equation 13 to I think 16. He inversed it. He proved it. The inverse is right too.
And
Yeah,
so
so
there it
that
is.
13 is the probability that what do you call it? The probability in terms of conditional probability, right? And then 14, 15, or it's the consequence of that. So yeah, I mean it's a joint probability as opposed to
Yeah.
conditional probability. Yeah.
But it's a state function, so how you arrive at it is going to be the same, right?
Exactly. That's the beauty of thermodynamics, right? It's a state functions. You can go either way, top down or bottom up.
Yeah. So basically, yeah. So this is the but if you can decompose the entropy into two parts. One is the whatever baseline, the coarser level, and then the conditional probability. And actually, it goes to the theorem that 16, 17 just kind of shows the consequence. Whichever accounting method you use, you'll get the same result.
Yeah. I was very happy. I was looking for that one. I'm not a statistician, so I couldn't prove it. Then he said it's easy. He just scribed it on paper. He sent to me. That's it. So I put it in the paper.
And it would have to be. It would have to be the same, right?
Yeah, exactly. But you have to prove it rigorously. I think that's just very important. That's 3 authors. You said a paper 3 authors. I wrote the paper. I have the idea. Second person is a statistician. The third person, that's what I mentioned. He worked on forest. He want to predict the wildfires in forest. That's the instability of forest. He also want to predict when the forest is in good health or bad health. But unfortunately, the life takes so many terms, right? Unfortunately, third author passed away the same year the paper was published. So we didn't continue that direction. If some of you want to study this ecosystem, we can work on that. I think I know that there are many people doing neuroscience here, right? Katerina is a neuroscientist. If you guys want to study the biology application, that'd be fantastic. We can think about how to work together.
Yeah. Yeah, actually, maybe, yeah, that's a good actually idea of that was actually my idea for future rooms, that I was thinking about bringing different people together that may be interesting to talk together, but even then in the future collaborate with each other. So I thought that would be very interesting for the future to have like this type of discussions, like so yeah. Yeah, it's
Okay.
interesting. We should chat more and maybe invite people from ecology, maybe Eli that I know, and some other people would be interested. I was at the Marine Biological Laboratory, and then there, the Oceanographic Institute in Woodsole on Cape Cod. They had actually also a team looking already back then with drones over the color of the leaves to in different seasons to calculate how climate change is changing that and things like that. Yeah, maybe we can invite people from different fields for application for your theory. That would be very interesting.
That's right. Okay. Well, I want to thank everybody. I got to go, and thanks a lot.
Thank you so much.
You enjoy
Okay,
it.
thank you
Thank
very
you.
much,
Thank you.
Professor Liu.
Okay.
Thank you very
Bye.
Bye.
much.
Thank.
Bye. Oh,
Yeah. Thank you so much, everyone, for coming and participating in this really great discussion and supporting us and asking great questions. Please follow the Science Society Club if you like this type of discussion. Tomorrow, I'm just saying a disclaimer, very most likely we'll have Dr. Chen talking about lithium use and the incidence of dementia. It's a very interesting study that looks at that and sees a reduction in dementia with people that use lithium. But there's some issues with setting up the Clubhouse account. But hopefully it will work out until tomorrow. So just a disclaimer. If not, I might just present the paper and but hopefully that it doesn't come to that. Then on Sundays, I wanted to start a recap room. So we are all busy during the week. We're in different time zones. So at around 1 p.m. EST, I wanted to summarize all the guest speaker talks we heard during the week, so people have another chance to look at the papers that we discussed and the topics and maybe ask some questions in case I can answer them. So I thought it would be good to have like a recap room of everything we learned during the weeks, because it's been a lot of guest speakers, and I think sometimes it's good to like summarize again. And yeah, next week we have a lot of interesting guest speakers again. We have Dr. Mackenzie looking at live cell chiral molecular interaction study, and then Dr. Fletcher, new method for training creativity that came out, and Dr. Lewis on Friday, Why Evolution Favors Symmetry. He's a mathematician and philosopher, and few authors, they published the paper, which is really cool, about evolution and symmetry. So yeah, thank you for coming, and I appreciate it. We have a lot more great rooms in the future that are planned until end of April now. We have every week a few guest speakers in all kinds of scientific fields. So yeah, follow the club. Thanks for coming, and thanks everyone.
Thanks,
Just
Ekaterina. So many interesting topics. I probably should do a cross sourcing as well. To recommend what. This discussion is so fascinating. Thank you again. Yeah. Hanson, you were.
yeah, no, this is great. Yeah, great session. But just want to add very quickly. I understand why Frank is talking about the equation 9 in that
Yeah, I see.
paper.
I
I
see. There's
understand
a
why
SK.
you.
Yeah. I got you. Yeah. We should.
Oh, okay. So you understand, right? So I don't need to explain. Okay, great.
Great, thank you. Yeah, and great questions, Frank, Hansen, and Serena, and Tuan, and everyone. So you guys make room. So thank you for your support. And yeah, I'm closing the room in 3, 2, 1. Bye, everyone.
Thanks, everyone.
Bye
Bye.
bye.